Good afternoon. This is going to be the hypothesis testing with means video 8.3, 8.2. I already forgot. I think it's 8.3. Um, just moving this so I can see it. Yes, this is 8.3. There's also 8.4 after this, which will be the same sort of thing done with standard deviation. So we're going to be doing the t-test a lot. Now, I wish they gave you t-tests with groups because t-tests with groups are so useful because sometimes you have the same amount of people in each group and things along those lines. But this will give you a good intro about like how t-tests works and what to do with them. Now, just remember that instead of relating it to a population mean, you could just have two separate groups. But then on the bottom, instead of your totals, you could have the different totals for both groups. So the way that they do it is fine, but if you want to, obviously go to that reading stats project that I made, and it will definitely help you. So here we go. Let's sharing the screen and let's get into it. So the first one is we're here in this giant set, and I'm gonna go to 8.3, testing claims about means, about a mean. Literally like with the same problems for all of these, but I'm fine with that. 1 through 4, 6, 11, 13. I'm going to do the textbook first and we're going to get into it. Hopefully everything is clear for us. If it's not, just let me know. I'm getting some more emails from folks. Just reach out to me if you need help. That's why I'm here. So I'm going to shut this 8.3 testing claims about means. And here we go. So testing claim about a population is one of the most important methods presented above. Yes, the t-test is the most important. This is the most commonly used one because you can do it for means of two groups, and that's usually every statistical test, like 90% of them. This section deals with a very realistic and commonly used case in which the population of the standard deviation is not known. Now, if we were comparing two groups, we would have the two different standard deviations, so we would know these, but the procedure when this is known is very rare. Okay, that's fine. In reality, it is very rare that we test a claim about an unknown value of mean, but we somehow know the value of the population standard deviation. That's true. When the standard deviation is not known, we estimate it by using our sample standard deviation. So for the central limit theorem, as long as we have the mean, we can break them down for the sample. All right, so we have the standard deviation, but if this is unknown, we can use the smaller standard deviation over the square root of n, which is used to make the t-statistic. All right, the three requirements are the p-values, critical values, and the equivalent methods. All right, so we can do the p-value method, the critical value method, the confidence interval method. I've only ever done the first two, like in the last video, so I'll learn the confidence interval with you guys, which is nice. These are all the pieces we need. There's our sample, mean, our sample size. S is your standard deviation of the sample. X bar is your sample mean. This is the population mean. We're going to use this for our null hypothesis. And that's it. All right. So as long as we got over 30 people and it's a simple random sample. And we're not going to do this bootstrapping stuff. All right. So here's our t-statistic. Done this a million times, but a lot of times this has the other mean here. That's very common, but this is fine. I do not mind one bit for this. It's a pretty standard formula. We're going to route it to three places. Use technology or use the t-distribution with degrees of freedom. So remember that when I went over to the last video, the degrees of freedom is n-1, and that's if we want to use the table. I'm assuming everybody's probably just going to use technology. All right, and then we can do with the critical values, which is also through the degrees of freedom. Okay, so normality with large samples, that is 30. So if your n is bigger than 30, it really doesn't have to be a normal sample, okay? Because it's such a limit theorem. That's what this means. Or if you have a small sample under 30, what should you do? You should do your QQ test and you should make a histogram. So if your n is ever less than 30, you should always do this QQ test. Or the other way you can do it, the other way, you could do the QQ test, or you can do what? Make a histogram. If it's a QQ test, the dot should fall close to the line. If it's a histogram, it should be bell shaped. Should have one mode, should not include outliers. Nice. Or we could throw them out. Is different from different sample sizes. The mean is t equals 0, but now the standard deviation is not 0. That's the difference. As the n gets larger, the t gets closer to the normal distribution. So the bigger you have, the more closer this is to a z. If suitable technology is available, use the p-value method of testing hypothesis. All right, so we have an example. I'll do it by hand, and we'll use the technology. So here we go. Here's example 1. Well, it already says our n is 12, so we would have to do a lot of stuff, right? First thing I'd have to do is my histogram and my QQ test just to make sure this works. But let's just say it is normal. Our sample is 6.833. Our standard deviation is 1.992400984. Common recommendation should sleep between 7 and 9 hours each night. Okay, so they give us a range. So claim that the mean amount of sleep is less than 7 hours. Okay, so should be 7. And then our alternative hypothesis says less than 7. So we can use this data to basically get our t-statistic, and then I'll show you that we can do this just with the other piece. So the t-statistic is 6.833 minus 7 over 1.9924, blah, 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 blah. And then we have to do this over the square root of 12. So that's going to be our first thing. So we know it's 6.33 minus 7 over this crazy long number, 1.9924, blah, blah, blah. And we have to divide this by the square root of 12. So this is what I ended up with as my t-statistic, negative 1.1648. Then I would look up using the table the exact amount and I'd get it. Now, what is a faster way we can do this? We can use StatCrunch, and I can go to a t-statistic for a one sample with a summary, because that's what we have. Our mean is 6.33. Our sample standard deviation is 1.9924. Our sample size is 12. We're trying to test this for a hypothesis that this is going to be 7. And it's one-tailed, so we want to know if it's less than 7. I also want to show that critical value to see if I got it. Let's compute this thing. The t-stat, negative 1.16, negative 1.16, I got the same thing. The critical value is negative 1.79. You get that from the table, okay? And this is not less than 0.05, so what are we going to do? Not reject this. So what does this mean? Average people, it's not less. We can't reject the mean, and this means that most adults do get that 7 hours of sleep every night. All right, let's make sure this is all correct. I think I got it. Oh, they give us the values? That's cool. I didn't know we had the values. So let's check it. We know this is sleep. Let's check out these values. Four, eight, four, four, eight, 6, 9, 7, 7, 10, 7, 8. So we need to make a histogram here. We also have to make a QQ sort to just make sure the data works. So I'm going to graph a histogram. I put in the sleep. I'm going to start with, I can start with 0. I can make these all 2. That's fine. Let's look at it. All right, let's make it 1. I don't know. Doesn't look great to me. I guess if I make it 3, it kind of looks more like a histogram. Oh, because it doesn't start there. That's why. Because the first one is 4 hours of sleep and not at 0. So I should start this at 4, and then I can do it by 1 each. And let's look at this. It still looks a little skewed. That's 3 and go to, I'm just changing the widths of these. Okay, I'll take it. Let's do the other one. Graph, QQ plot. I guess it's pretty close to a line. Let's see what they said. Okay, I'll take it. Theirs looks better than mine, but I'll survive. Okay, so that's the null. Oh, okay. I don't know why it's the same. I don't like it. Does not contain the condition of equality, becomes the alternative hypothesis. Okay, that's fine. They got negative 2.9. What did we get when we did this thing? Oh, it should have been 6.833. So let's change that. And that's the right one, negative 2.9. Let's go to the testing and the StatCrunch claim. Well, we can say because we have the data, you know. Hmm. I didn't have the group by on. That was my mistake. I wanted to see the critical value. Okay, there's something happening that's wrong. Well, let's try it a different way. So I'm making a mistake here. Let's go to T-stats, one sample with summary. There's the negative 2.9. There's your critical. It's still not significant, okay? Now, how come I was not getting this when I was doing it the other way? With data, okay. There's my data. When I click compute, it's doing all of these one at a time, but it's not giving me stuff for these other values, which is weird. They're separating them all. All right, let's see what this says. Down, reject the null. 0.3865. Yeah, okay. I'll take it. Maybe that there's a different way to do it with the data in there. One sample T hypothesis test. All right. That's our stat crunch. That's what it should look like. So one sample T hypothesis test. One sample T hypothesis test. One sample T hypothesis test. And it just says mean of sleep. Let's actually just highlight this and try it again. Maybe if I have it highlighted. Yeah, okay, so I have to highlight the data. That's the only difference. Okay, I'm fine with that. If you highlight the data, then you'll get the right answer. Perfect. And it looks exactly like this. All right, let's keep going. Example 2 is a left-tailed test. Okay. With the t-statistic rounded to negative 2.9. Size of n is 12. The degrees of freedom is 11. Table 3 shows the values, examples. Okay. So this is just if we didn't have it. We actually have to look at the table. So I'll show you table A3. I'll show you how it works. Table A3. Here's your t distribution, and they say that t statistic is negative 0.290. All right. We have a degrees of freedom of 11 at it's one-tailed. So this is your example 2. T is negative 0.290 degrees of freedom. So if n is 12, this is 12 minus 1, which is 11. And we have the p-value, which is 0.10. So this is going to show us that if we have this value, But the technology provided a p-value of 0.3887. And we're testing this test statistic. Okay, so let's see how it looks. I know I did it in the other video, but I just thought I'd try to show it again. Our degrees of freedom is 11. And we're talking one-tailed at 0.05%. I got 1.796 as the probability we should be looking at. One tail, 11, 1.796 as the critical value that we need. What did they get? Examine the values of t in the row for 11. You'll see that 2.90 is less than all the t values listed in that row, which indicates the left tail is below it. Okay, so this value we got was less than all of them. That's the way that they did it. But technology gave us 0.3887. Conclusions are the same. I don't really like it because using the range, it can be tricky. The critical value is probably better. Sweet, let's do the critical value method. You can use the table if you want. It was just not making sense to me. So let's make it happen. I like using the critical value method or the p-value method. Tables never really make sense to me when I'm doing them. I mean, they're there, they make sense. I just get confused sometimes. All right, so here we go. Sample one is a left-tailed with a t statistic, and the sample size is 12, which makes it 11. Significant levels of 0.05. Refer to the row of table A3, 11 degrees of freedom, area one tail. The intersection of the row and the column yields a 1.796. All right, so I might as well just have another Pearson here. Do I have another Pearson here? Just checking my mail for a second. Okay, cool. Let's look at Pearson again. So we have the table right here. Might as well get this table right before we start doing the problems. We're talking critical t values. Here it is. And they're telling us degrees of freedom is 11. And we want this for 0.10. It's a left tail, so it's a one tail test with 0.10. Should be the last one. So I got 1.363. We see that it is 2.90. Oh, because it's on the other side. So area in the one tail. So we have to cut this thing in half. So if we say it's 0.10, it's going to be the same thing as what? 0.05. Examine the values of t in the row for degrees of freedom to see that 0.290 0 is less than all of those indicated in the row. 11, yes, it is lower than all of them. I don't like it. All right, so here we go. So here's 11 and 0.05 for one tail. 11 and 0.05 is 1.796. That's what I thought it was good. I just wanted to make sure. So there's our 1.796. The intersection of the rows, but this test is left tail, so it's negative 1.796. Cool. Just want to make sure that worked. Did I lose my notebook? All right, here's where we were. Okay, so now figure A-H is its institutions of this does not fall outside of the critical value. So we got this value when we did the stats, right? The negative 2.9, right? This negative 2.9 is not more over than this one, the negative 1.796. So that is why we failed to reject the null using this way. All right, let's do the confidence interval with the E. Something new for me. Example 1 is a left-tailed test with the significant. Okay, so we got left-tailed. Our alpha is 0.05. We want to be 90% confident. And then we have this, which says 5.8 to 7.9. In testing the claim that 7 hours, we use HO is 7 hours, but we assume that this is telling us 7 hours could affect it. We don't have significant evidence to reject it. $5.8 and 7.9. Is that what they gave us from before? All right, so we got to find the error again. So if we find the error again, we should be good. We have these values to get the error. And once we have our error, we should be able to do this. So I'll just go back here and look at the error for this one. Okay, that's how we did error for this one, but how do we do the confidence interval for estimating the population means? So I'm going to go into 7.2 and see exactly how they got the error, which they claimed was 5.8 and 7.9, which is totally fine. So it's your T statistic times the standard deviations divided by N, which isn't too crazy. That's how we get the error. This is how we get the T statistic, which we already have. So it's T statistic times S over the square root of N. No, it's the T statistic times S over the square root of N. So we already have our T statistic, which is negative 2.90. Our S is the standard deviation. Which is 1.9924. Our N is the square root of 12. So we have, this gives us our error per confidence interval. So our error is negative 1.67, right? So all we have to do is take that original average, which we know was 6.833. What is 6.833 minus 1.667? There, well, I only got 5.1. 6.833 plus 1.67. And I only got, and yeah, so mine's off. So let's find where the mistake is. So it says we need the error. Okay, because we don't use, we use the test, we use the one tail or two tail, mu, this varies. Okay. So we have to get this value. We have to get our t-statistic value first. So I was using the critical value instead of the t-statistic value. That wasn't using the right one. So the t-statistics value, we just got it from that chart, didn't we? I believe we did. So the t-statistics value is this 1 point whatever. Where is it? We're already hiding from the negative 1.796. Right. So that's the critical value. I mean, we have to put this critical value here. This is negative 796. That's what gets multiplied by it. Sorry about the mistake. We need this critical value, not this one. Negative 1.796. So it shows us that our error is in fact negative 1.0329. So we take the mean, we add, we subtract negative 1.0329, and then we add 1.0329, and this is our confidence interval. I got between 5.8 and 7.86. And what did they get? Five point eight and 7.86. Yes. Okay, so that's how they do it. So you have to use the critical value. I just forgot. I was using the test statistic. Keep confusing test statistic and critical value. So let me make that really clear. Okay, so this critical value is the one we're using. The test statistic is the one we've got. So we have to test it based on the critical value. I wish they would use a different letter, but they don't. I know that's annoying. All right, so the preceding examples are based on the left test. The following example is a mean for a two-tailed test. Cool, let's do a two-tailed test. Okay, so here's example 5. All right, so we have n, which is 106, which gives us a degrees of freedom of 105. Our sample mean is 98.2, and our standard deviation is 0.62. I have a big enough n where I don't have to worry about things. Oh, sorry. And I'm just going to type it right in. So we don't have the values. So I'm going to do stats, t-stats, one sample from summary. My mean is 98.2. My sample standard deviation is 0.62. Our sample size is 106. And our hypothesis test is, we want to know 98.6. And is it lower? Yeah, it says it's yeah, so we don't know which way it goes. So it's 98.6. And I want to show the critical value. Compute. It's significant. There's our t statistic. There's our critical value for t. We're good to go. We've got the whole thing. We've got everything we need to solve it. Here's your null and alternative hypothesis. They got negative 6.64 using the formula, negative 6.64 using the StatCrunch. These are critical values, plus or minus 1.983. If we use the table, our degrees of freedom was what? Our degrees of freedom was 105. 100, so they don't really have it. So it's got to be close to the 100 mark, and we know it's going to be two-tailed. So that's how they got the value. One 1.983, 1.984, right? Ta-da. We just 105 is closest to the 100. 106 is closest to the 100. 105 because it's degree of freedom is close to the 100 mark. There's our interpretation. When it's knowing reality, it's very weird to claim about a knowing this. Okay. The key elements, standard. This is when we do actually know that population. All right, let's do the problems. Cool. Hopefully that was useful, but it's time to knock them out. 1 through 4, 6, 11, 13, 14. All right, here's number 1. Listed below are the salaries of millions of dollars for basketball players. What other requirements must be satisfied for a mean? All right, so we have to tell if if it's normally distributed or not. I already don't think it is because we've got an outlier here. We throw out the 36, we'll be fine. Well, I can look this up. So this appears to be an outlier. Let's at least see if it's normally distributed, but I don't think we're going to be able to do number 1, which is fine. So just open a StatCrunch over here. One, 2, 2, 2, 2, 2, 2, 4, 4, 6, 7, 9, 12, 36. So if we make a histogram and we start with 0 and we got to go by, I guess I can go by 1 each. Yeah. Doesn't really, it looks like it's left skewed. Even without the outlier, it still doesn't look like it's normally skewed. Then if I do the QQ plot, you'll see that it's off. Yeah, that's off. All right. So it's got to be either greater than 30, normally distributed, and from a simple random sample. That's the answer to 1. Is it? Nope. So I gotta reload this. So 1, your n should be bigger than 30. It should be simple random sample. It should be normally distributed. If it's not, and this is no, we can't do it. So if we are using the sample from exercise 1 for a t-test of the population claim that the mean is greater than 5 million, what does the degrees of freedom notate? All right, so the degrees of freedom is just n-1. It just means we'll be able to get all the other scores while losing one. Because if we take one out, the average will just kind of tell us what that's going to be. And they have a much better definition in here, and I feel like you should write that. So I want everybody to write in the definition. But basically, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Our degrees of freedom here is 14. It basically just means we can get all of the values when one of these is missing. Exercise 2 refers to a t-test. Okay, what is a t-test? What letter? Why is the letter T used? What is unrealistic about the Z method described at the end of this section? Okay, so what is a t-test? It's a comparison of means. Why is the letter T used? I don't know, forgetful. Oh, okay. So this is our buddy from the Guinness. So it refers to the student T distribution from that guy from Guinness. The z-test method, it's basically all the standard deviations are the same, but this one we realized that the standard deviations change, and with bigger ends, it gets closer to the z. That's what they mean. Or gets closer to normal. Basically, the only difference between the z table and the t table, the mean is still 0, but the standard deviation varies, and it should vary. All right, here's number 4. The statistics for the sample of data in exercise 1 are boom, 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 where the units are for millions of dollars. Find the test statistic critical value for a test of the claim salaries. Assume that it's used. Okay, so we might as well do this, right? I'm just going to do it via StatCrunch. If you want to watch, you can rewind to watch me do it by hand if you'd like. The sample mean is 6.13333. Your standard deviation is 8.862978. Our sample size is only what? 5 people? 15 people. And we want to know it's $5 million. And we're testing if it's going to be greater than $5 million. Compute. It is not significant. What a surprise. So what did they want? Find the test statistic critical value. Okay, so your test statistic 0.495, our critical value 1.76, our p-value is equal to 0.3141, not significant. So we will fail to reject the null. Everybody's salary is going to be around 5 million. That's what it means. All right, that's 1 through 4. Let's look at 6, 11, and 13. Let's start with 6. So either use technology or A through 3. What's the final conclusion? So your null hypothesis is the mean is equal to 2.5. We have an N of 37, which is good, and we have a test statistic of negative 0.331. And we're using what? I guess I'll just use 0.05. This is a two-tailed test here. Right, this one's a little weird. Let me do 5 first, because they're not giving us a lot of information, which I don't like. Let's see what they got for 5, and I'll work backwards. So for number 5, we have a sample size of 40. We have a t-statistic of negative 3.135. This is my t-statistic. It should give me that value, right? It should give me the value. We should see if this is greater than 0.05. So find the range of values of the p-value, right? So n is 40, which means this should be degrees of freedom of 39. And then we have our t-statistic. Guess I got to use the table. So if we have a degrees of freedom of 39, and then this says it's negative 3.35. This is bigger than all of these. So I think that makes sense for why this one is significant, because it's bigger than all these values for the 39. So it doesn't matter which one you are. Let's see what 5 says. 5 says the p-value is 0.0033. How'd they get that? Yeah, it doesn't let us go backwards on this. Let's see if we can do it on Excel. So they said that they want us to do it with this mini tab thing that I don't have. Excel, p-value from a t-statistic. This is if we have the data. We can simply enter the value. Okay, here it is. Three ways to find a p-value from t-statistic. In each of the following examples, we'll find a p-value for our right-tailed test. Okay, the first way to find it is to use an online calculator like the t-score to p-value calculator. Okay, so it's just a calculator. We can use a distribution table and see what it falls between. So here we have degrees of freedom of 39. Now it stops here. Okay. A TI 34. So it doesn't have it except for a specific one. So I might as well just go here to a t-score to p-value calculator, because that is what they're pretty much asking me for. So for 5, our t-score is negative 3.135. We have degrees of freedom for what? 39. This is it's equal to it, so it's two-tailed. Most likely it's 0.05. Let's calculate. 0.00326. It is significant. Cool. So 5 is significant. Is that what it says here? 0.0033, 0.0033. Nice. Cool. So let's do the weights of pennies. Our t-score is negative 0.331. Our n is 37, so this means 36. This is also two-tailed. 0.7425. It's not significant. I didn't think it was going to be significant, but now we have the answer. .743. So for number 6. Usually, we don't have these values without actually having the data. So without the data, it makes it way harder to do them. Now let's go to 11. Using 0.05, get the critical value in the conclusion. Is that above here? Tower of Terror set 33 lead times of 5 p.m. using the first 40 times. The accompanying Excel display is contained. So it's not significant. All right, so they shove this into Excel with the data. So 11's not significant. The critical value is 1.685. The test statistic is 0.940. This is not above this. So it also gives you the p-value of 0.177. Either way, it's not significant for 11. You guys can write the conclusion, which will be fine. All right, let's go to 13. Well, I can see if I did that right. Oh, fail to reject the null. Perfect. I like it. Let's look at 13. It's 13, right? 13. All right, here we go. So our n is 300. Makes our degrees of freedom 299. Our p-value, we're using an alpha level 0.01. Our x bar is 122.96. Our standard deviation is 15.85169. Use this to claim that the sample with a mean greater than 120. So our null hypothesis is that our mean is equal to 120. Our alternative hypothesis is that our mean is going to be greater than 120. And that's pretty much it, right? So let's just let the calculator be our friend. We could do the whole thing by hand, but we might as well just use it since it's right here. So our mean is 122.96. Our standard deviation is 15.85169. Our sample size is going to be 300. It's a one-tailed hypothesis, but we're talking 120. We want to be bigger than 120, but we're no longer at significance of 0.05, we're at 0.01, and that's what we need. This is significant, yes, so we can reject the null, our t-stat. And you should be doing this for all of them. Just copy this thing. And just obviously just paste it directly into your answers. But we should know this is not significant, okay? There it is. So you can just copy and paste it. What we care about is this value. You could think because this one is less than this one, that's why it's going to work. You can look over here at the critical values, you can look at the p-values, but either way, you get the right answer. All right, I hope that was helpful. I think I'm going to do one more so I can knock out this entire set of the 8s and enjoy your day.